Lesson 4-2, graphing polynomial functions. So polynomials, we still have some function of x to be x to some degree, like x to the 4 here, and we got this whole polynomial going on, right? Whole number of powers of x. Okay, now we're going to graph these and look at properties of graphs. So maybe what are maxima and minima, what are x-intercepts, and then graphing calculator gets really helpful here. I'll show you guys how to use Desmos to take tables of values like these and put some kind of regression through it. It could be a linear regression or polynomial regression. And so based on tables values. And these are particularly interesting for like actual data. So here we're looking at backpack sales in dollars as a function of years since the year 2000. So okay, so we can make actual equations out of this actual real world data. And so that's exciting. And so let's start off real basic, real fundamental, and work from there. So they give you this classic looking polynomial. We got y equals x to the 4 minus 2x to the 3 minus x squared plus 1. Okay, okay they're saying draw the graph by making a table. So, hey, look, this is just like the tables I had you guys draw. Right? We have x values. They go from -2 to +4. Here, and let me show you if these work out. I'll pick at least a point. So here, I'll use my answer trick. Answer to the power of 4 right there, minus 2 answer to the power of 3. Every answer is just standing in for some x. Right? So minus x or answer squared, and then plus 1. Okay? Now, if I pick a value like -2, right, so now I calculate saying, okay, so something about -2 here, and I plug that in, I should get 29. Let's see if I do. Oh, point, it's 29. How about -1? I wonder if I'm going to get 3. Oh, yeah, it's 3. Let's try 0. Yeah, 1. Okay. Here, I'll go all the way to the end. If I type in 4, it says I should get 113. Right, and then point 113. Okay, so here, you can do that for a whole list of points in this table. Right? So we're getting 7 coordinates out of this. 7 coordinates. Right, and of course you could plot. So to the left, that's -2, go up 29. Right, -1 up 3, 0, 1, right, all the way to 4, 113. Here, and I did go ahead and I have a bunch of these queued up in Desmos, right, all the examples that I want to do. And so there's the function, and if you plot all those points, okay, and then connect all the points, it looks like this. If you get more granular, so here's 0, 1, that was one of the points on the table, okay? Right, so you can get more granular if you have to. You can plug in like what if x is 0.5, you get the value, right? Or just run to a graphing calculator like this. And so what are some interesting points in this graph? Well, how about extrema? I see an absolute minimum here where x is 1.78 something, y bottoms out at -3.4 something. Okay, so that could be an absolute minimum, right? Uh, I see a couple of x-intercepts. So here's an x-intercept at where x is 0.72 or where x is 2.3 something. All right, so that's where y is equal to 0. I also see a y-intercept where x is 0, y is 1. Right? Those are probably the main features. And then how about in behavior? I think if x goes to infinity, that's to the right. Y goes infinity up. Right? And if x goes to the left forever, -infinity, y still goes to positive infinity up. Right? No surprise there because the degree is 4, which is even, and the leading coefficient is 1, which is positive. Right? So yeah, so of course it takes that shape. And so I think that makes sense. And I'm going to minimize this. I'll just minimize it as we go along. Have it stored somewhere. You come back to it. Yeah, that'll take care of that. Okay. Example 2, identifying extrema. The same thing, they give you a polynomial. We got x to 3 plus x squared minus 5x minus 2. They're recommending making a table, plotting points, and then being able to answer the question from there. Those same things before. I'm going to plug into my scientific calculator. Okay, x to the 3 plus x squared minus 5x minus 2. Wait, first answer is jump, don't worry about that. And then what if I plug in -4? Okay. And then scroll up and pop that in. Let's see if I get -30. Oh, it's -30. Oh, yeah. Okay, I'll try 2 more points. What if I plug in 0? Do I get -2 here? Oh, yeah, -2. And what if I plug in 3? I should get 19 out of this. Let's see if I plug in 3. Oh, yeah, it's 19. You plug in all these values. Okay. Supposedly it makes this shape. Let's see, I think I put this one in Desmos also. X to 3 plus x squared plus 5x. See if I see that one. Do I have x squared? Okay. Here, let me pop that in Desmos real fast. Boy, there you go. That's exactly what that function looks like. Okay, I remember why I did not have that ready in Desmos ahead of time because the book gives it to you right here. Look, it's the same graph. Oh yeah, it's the same graph. Okay. And so what are some maybe interesting points? Right, so locations of extrema. So I see an extrema. So here's a relative max here. Here's a relative min here. Right. How about intercepts? I see 1, 2, 3x intercepts. There could have been up to 3x intercepts because there's a degree of 3 that allows for up to 3x intercepts. And there's also a y-intercept here. It looks like at 0, -2. Now, if I pull up the Desmos version of that, is that, okay, this one right here. See, if I hover over the points, it should tell me what they are. Yeah, there you go. There's the x and y coordinate of that relative max, the x and y coordinate of this relative min. Okay. Here's a y-intercept here, boink. And then here's your x-intercepts, boink, boink, and boink. Yeah, so you get all that information. Okay, actually, here, I'll just go ahead and exit these out as I go along. All right, so otherwise I'll have these graphs building up. Did I do that one already? Okay, yeah, we did that one before. Boink, and boy. All right. Yeah, so that's pretty good. Number 3, or example 3. Oh, the total number of certified pilots in the United States. And it's degree 4, so it's x to the power of 4. Okay, now we're getting like a real life example. Right, so yeah, you could plug this in. You can plug in values, but no, x is the years after 1930. So year 0 is the year 1930. So it looks like, is this, okay, pilots in thousands. So 7.708, that means there were 7,708 pilots in the year 1930. 1930, about 7,000 some pilots. Right, if you go ahead, here. All right. All right, we're back. Had to fix something there. All right, so 10 years after 1940, that would be 10 years after 30 would be 1940. There were 131,000 pilots. Let's go ahead. How about 70 years after? So the year 2000, there were 650,000 some pilots. Okay, so you can plot this all on a graph, and look at that. It goes up for a while, then then it comes back down, goes back up. Huh. I wonder, see, how could you make a polynomial off that? Goes up and then down and up. You probably need at least a cubic to model that pretty well. Right, so something like a cubic. Right. So they don't really prompt you, I think, to try to create an equation there, but they do with this next one. I do have this next one ready. Okay? So very similar idea. We got a table of values. Now this is millions of backpack sales by year, starting at the year 2000. So I could call the year 2000 year 0. Okay. And then, these are all in the thousands, these backpack sales. Okay, so I was having trouble truncating the axis in Desmos. So the solution I found was to divide by 1,000 and just put the sales in billions, something like that. Okay. Now let me show you what I did here. I'm going to start this from scratch. Okay. Desmos. Right, I'll show you guys exactly what I did. Now, there are different ways to do this. The book, I think, prompts you. Does the book prompt you to? Hang on, I got to fix this. Fix. All right, back here, got some technical things going in the background. And so here, I know everybody has different type calculators. Suppose you have a TI-83 graphing calculator, for example. You can Google how do you create a regression. It'll tell you exactly how to do it with like list 1 and list 2 and stat. And there's a process. It'll tell you exactly how to do it. You can do that. I also found. Let's see. I did a general Google search. I found a regression calculator. Right? You can type in tables of values, so X values and its corresponding Y values, maybe the year and millions of sales. Right? And oh, look at this. It'll create a polynomial for you. And you can choose the degree. Oh, here it is. See, it says degree 2. So that would create up to a parabola. But if you could change that degree to like power 3 or power 4, you can create different kinds of polynomials. So bump that. Right? And then how do you do that in Desmos? So, guys, you got to type the word table. You can Google this too. Actually, because that was so fast, I'm going to redo that just in case you missed it. Type the word TABL. No, as soon as I hit E, it's going to, bam, open up a table. See that? I type table, it opens up a table. Okay? I start typing in this data. And I did that ahead of time here, so let me copy some of my points. So from 0 to, okay, so look at years after 2000. So 0 years after 2000, 1 years. Okay. And look, all I'm doing is hitting enter, and it's already telling me, okay, you're probably counting by ones. Right, 7 years after 2000. Okay, so okay. And then Y values. Okay, now I need sales. Now notice I put this in billions of sales. Your book has millions. I put billions, so I can put this all. Okay, 1.14 billion sales. So I go here, type 1.14 billion sales, and then my next one. Okay, I can do that all the way down. Okay, so, so let's say I filled in all that table right there, got all that. Okay. It's going to create like a scatter plot. You guys see all these points right here? Now, let me get rid of this so I can show you guys how I created this from scratch. So look, I'm going for a 4th degree polynomial. Now, I had to make that up. So let me get rid of that. Boink, that's gone. All right, so now back to my scatter plot. So I didn't just click down here. Right? Okay, so how do I make it create, say, like a regression model? So you type y and then _1. Right? So it says y1. So you just have to do it this way. Just follow this if you want to do this on Desmos. Then you get the tilde symbol. You guys remember, yeah, tilde? Or so, in physics, I use that oftentimes to represent a direct proportion, but this math class will let you make a regression, right? So then I need a leading coefficient. I'll say A, and I'm going to have Desmos tell me what A is. I need x to the underscore 1. It's just a thing you do. And then right key, and then to the power of, well, what kind of polynomial do I want? Now, I could maybe approximate this with a parabola, maybe. And if I want to do that, I'll do x to the power of 2, right? Oh, but yeah, that doesn't look very good. So maybe I'll do plus b x underscore 1, it could be to the power of 1, which is already there anyway, right? And then plus c, right? Hey, that's not too bad. Look at that red parabola. Now, that is a parabola, and look, it tells me exactly what a, b, and c are that will best match that scatter plot data. Now, if you want to, you can get more granular. I'm looking to see, it kind of goes up and then comes back down, goes up again. I think a fourth degree polynomial would be a better representation. So I'm going to change some of these. So instead of x to the power of 2, let's go to the power of 4. How about to make a fourth degree polynomial? Then I'll put this to the power of 3. Then I'll plus cx underscore 1 to the power of 2. And then plus dx underscore 1 to the power of 1. Okay, actually, you don't even need to do that. Okay. And then, no, I would say plus e, but you have to be careful because e is a special number in math. It's called 2.71828. Right? It's a very special number. So you don't want to type e because the calculator think you're trying to talk about 2.718. So I'm going to type f. Right? And then it actually will give me a value for f, which is 1.1. Okay, there you go. And look at that. Okay, yeah, I think it's a little better. Okay, so here, fourth degree polynomial. See how it rises a little bit and it comes back down, kind of follows my scatter plot a little bit better than the quadratic did, than that parabola before. Yeah, so that looks a little better. And so that could estimate that data. So I could get some information from this. Like I could model, I could say like, hey, how about 20 years after the year 2000? What would I expect? So if I could extrapolate and I could follow this curve out and say, well, okay, I think it's probably going to be maybe sales go way up after this. Looks like you're starting to kind of rise at the tail end there. And so I think that could represent that. Okay, so start with that, with that. Whoops. All right. All right. So yeah, I'm going to close this out and yeah, just keep going. Like, goodbye. All right, so that's how you create a regression. Here, I will do some. Oh, here it is. Your book does tell you on a standard graphic calculator. It says stat plot, use x list and y list to get the xy coordinates of all the scatter plots. Okay, and then how do you create a polynomial? Okay, it tells you exactly how to do it. Now I show you on Desmos with both a 2 degree and a 4 degree polynomial. Okay, so I show you Desmos how to do that. If I ever want you to graph something, I'll allow you to use Desmos or use the graph calculator if you like. All right. They got another example here with, say, oh, actually, no, I think it's just a continuation of before. And so let's jump into these. Determine the consecutive integer values of x between each real zero occurs by using a table, then sketch the graph. Right? So it gives you some polynomials that we're trying to find the x-intercepts basically, and maybe they don't want exact decimal values. They just say, okay, between 3 and 4, across with the x-axis, something like that. Between x is 3 and x is 4, for example. Right? So I went ahead and plotted this in Desmos to begin with anyway. What we got here? Uh, x squared plus 3x plus. Okay, yep, I got it right here. Right here. Come on, drag over here. Ready to go. Right. So I plotted that ahead of time. Yep, it's a parabola. No surprise. Looks like guys, you could totally create a table of values. You could say, what if x is 1? Say 1 squared plus 3 times 1 is 1 plus 3 is 4, minus 1 is back to 3. So the point 1, 3 should exist. So you go over to 1 comma 3, which is right there. Make a point. Right, how about 0? When plugging 0, you get 0 plus 0 minus 1 is negative 1. 0, negative 1. Right? Okay, so you could do that all day. Right? Create a bunch of points. Nice big parabola. Right? So I see some x-intercepts at, negative 3.3 and 0.3. So if you throw in a graphic calculator like this, you can get pretty nice exact answers. Okay. Now, what if you make a table and you're just counting by integers? Maybe the best you could say is between -3 and -2 and between 0 and 1. Okay. Let me go ahead and make a proper table with you guys here. Make a proper table. Okay. So I'm going to type this function into the scientific calculator by doing the answer squared plus 3 times the answer minus 1, where answer, of course, stands for s. Okay? Let's make a table. So I'm going to go, what are some x values, y values? Okay? Now, I saw, of course, the actual graph one does look like a really nice looking graph. Okay? So I kind of have an idea of how to frame this question. Let's go -2, -1, 0, 1, 2. Wait, did I scale it right? Make sure. Sure, double check. Got it. Okay, actually, no, I need to go back a little bit more. Go back a little bit more. Okay, that's all right. I got room. All right, -3, uh, -4. Okay, so something like that. Okay, 1, 2, okay, that'll be plenty good. All right, x, and I'll put my y-axis here. So let's go -4, -3, -2, -1, 0, 1, 2. Okay, let's plug each of these into this expression and figure out what are the y values. So I get -4, scroll up, plug it in. I get 3, yay! -3, plug that in, get -1. -2, plug that in, get -3. -1, plug that in. Also -3, 0, plug it in, -1, 1, plug it in, 3, 2, plug it in, 9. Okay. I can plot all those. So it looks like it goes down to -3, but it also goes up to 9 here. Here, let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I kind of squashed my y-axis a little bit just to fit it. -1, -2, -3, -3 is like down here. Okay, so we got -4, +3. Switch to peak. So, right there. -3, -1. That's down here. -2, -3. It's like down here. -1, -3. 0, -1. 1, 3. 2, 9. Okay. All right. So, okay, yeah. Parabola, no surprise. So it's like, yep, that's looking like what Desmos was telling me too. So I could say that the x-intercepts, well, there's one x-intercept between between x equals -4 and x equals -3. Right, so it's like somewhere in here in this interval. Okay, and also between x equals 0 and x equals 1. So kind of somewhere in this interval. Okay, that's all the book is looking for. Saying, okay, so somewhere between those integers, somewhere between those integers, that polynomial crosses the x-axis. Right. Let's try it for this one. Here, I did a proper table with you guys. So you guys do see how to do this method, right? Okay. If you can't graphically get an idea, maybe that could be helpful just to figure out how to frame it. But you can create a table, make a bunch of x values, and at some point, actually you can read straight off the table if you know how to read a table. See between -4, where x is -4 and x is -3. See how y switches from positive to negative? And then from x is 0 to x is 1. See how y switches back from negative to positive? Ooh, that would also tell you that there are x-intercepts because y is switching from positive to negative, negative to positive. It has to be crossing the x-axis. Right? As long as it's a polynomial, that would have to be true. Okay, so here, these next few, I will just pull up a Desmos graph. Right. So x3 plus 4x squared. I think I got this one keyed up. Yeah, it's right here. So here's the next one highlighted. This is number 3. Look, it looks like this, right? So, okay, I see. Here's the exact x-intercept at -5.15 something. So if I did a table method, I could say, see if I plug in -6 for x, I'll get a negative value. If I plug in -5 for x, I get a positive y value. So therefore, this polynomial has to cross between -6 and -5. So it's -5. Okay, so I got that. If there was a question about relative extrema, here's your relative max here at this coordinate. So -3.129 point something. And here's your relative minimum where x is 0.5 and y is 3.6. I'm rounding a little bit, but you guys get the idea. Oh, and here's a y-intercept. Ooh, 0.5. Okay, so all those are interesting, maybe key parts of the graph. Got some end behavior, goes up to the right forever, down to the left forever. No surprise, because we have a odd degree. Yeah, and a positive leading coefficient. Got all that. All that is all right there. Yeah. All right, next one. Now these next two, actually what it does prompt you to do is to estimate the coordinates for the relative max and relative minimum. So here, I'm pretty sure I got these also plugged into Desmos ahead of time. Yeah, -2x to the power 3 equals 12. Yeah, okay, got this next one queued up right here. Boom. right? Of course, you could create a table and eventually make your way to craft this graph anyway. Okay? But what are some properties? Now, so they were looking for extrema. So here's a relative minimum. So x is about 0.36 and y is about negative 1.4 something. Okay, something. And then a relative max here at x is 3.6 and y is like 33. Ooh, something like that. And so some other parts. Ooh, I see three x-intercepts, 0, 0. Actually, 0, 0 is both an x and a y-intercept. Ooh, right? We get this x-intercept at x is 0.76 and this x-intercept at x is 5.2. So, right? So all those are interesting features of the graph. Right? And then end behavior goes up to the left forever and down to the right forever. That's because there is an odd degree. So in this case, x to the power of 3, that's an odd degree. And a negative leading coefficient. See how it cares. If I change this, if I make this positive, boom. See how the graph just flipped upside down? But if I put it negative, boom. Hey, it goes back to how it looked before. But there you go. Just like that. All right, boink. Goodbye. Next one. F of x is x to the power of 4. Now, right away, guys, the degree is 4. So I bet it's going to look sort of parabola-ish. Maybe kind of resemble that. See, x to the power of 4. Okay, got that right here. Yeah, sort of. Okay, now again, this is not a proper parabola because parabola you need x to the power of 2. Right? But this x to the power of 4, it sort of looks similar, right? Goes down, comes back up, right? So there is an absolute minimum right here where x is negative 0.79, y bottoms out at negative 2.19. Yeah, so there's your coordinate of your absolute minimum. There's also this y-intercept here, 0, negative 1. No surprise, because if you plug in 0 for x, you get negative 1. So that's that point there. And there's also a couple of x-intercepts if they ask about that. So where x is negative 1.39, where x is 0.47, yeah, that's where y zeroes out. And so we got all those properties of that graph right there. Goes up and to the left forever, up and to the right forever. So there's your end behavior. Yeah. Boink. One more down. Example 3, business. A banker models the expected value of the company in millions of dollars to be, see, value is n to the 3 minus 3 and squared, where n is the number of years in business. Okay, so if there's 0 years in business, well, we can definitely get that point because if you plug in 0, you get 0. So 0 value during year 0. He opens his doors, it's worth nothing. Then we're going to roll forward the years. Year 1, year 2, year 3. See, I could, again, go back and make a whole table. I could plug in n as, well, starting at 0, because start at year 0. But 1, 2, 3, 4, 5. Let's see, v value. It's going to come out with some value. Again, I had Desmos do this ahead of time so we can see exactly what this looks like. Right, so you can plug in values. So 0, you get 0. Yep, just like I said. It looks like this point, if you plug in 2, you should get negative 4. Let's try that out. 2 to the 3, that's 2 times 2 to 2, that's 8. 2 to the power of 3 is 8. And then 2 squared is 4, 3 times 4 is 12. Guys, what's 8 minus 12? I think it would be negative 4. Yeah, boink. So there's a point. You can put that on a table. Anyway, if you make a bunch of points, it eventually makes this curve, right? X to the power of 3, no surprise that it goes up, comes down, goes back up again, so it could totally do that, right? And the way to interpret this, I think that the proper domain would be to start at x equals 0 and go forward because the business didn't exist before it opened, right? So none of this negative territory actually matters, right? In terms of x value, right? And then the y value, remember, it tells you the value of the business, right? So it starts up being worth nothing. It looks like during the first couple of years, the first 2 years, it was like losing value, losing value. At year 2, it bottoms out. So now he's like deeply in debt, but maybe he's sort of like gaining customers or he's like waiting out the rough period. Okay. So then right here at year 3, at the end of year 3, by the time the end of year 3 rolls around, he's been operating his business for exactly 3 years. Now his business is back to worth 0 again. But look, it's part of an uptrend. So year 4, like if you plug 4 in here, say 4 times 4 times 4, it's like 64. 4 squared is 16. Here, I need to plug this in my calculator. What is 4 to the power of 3 minus 3 times 4 squared? My calculator is saying 16 units. That was in, what was the unit there? It was in millions of dollars, right? So at the end of year 4, his business would be worth $16 million. Ooh, right. So, right, and it's just going up from there. So I think the domain would be from 0 to infinity if you could just keep running his business till the end of time, sort of thing. Okay. All right. So yeah, key features of domain. Right. Okay. Yeah. So you saw this. You saw the the minimum, the absolute minimum, right? You guys saw where it's crossing the x-axis, the time axis. That's to say, like where it goes back into the black, it stops being in debt. Yeah, all that, or it stops being having negative value, I should say. Like number 12, population of Cincinnati, Ohio since 1960. Oh, look, we're getting one of these scatter plots. Okay, so they're giving us the table. I think they want us to find an equation, right? So the coefficients of regression, say 2000 is probably something like that. So they give us these years. So 1960 all up to 2010, the corresponding population. Now, you do see the population of Cincinnati is decreasing. In 1960, it was just over 500,000, and then it steadily decreases after that. So I showed you guys how to do this. Right? So as a reminder, here, I've got it all set in here already, but I'm going to remind you guys exactly how I did that in case you either missed that or forgot. So Desmos graphing calculator. All right. So first thing I typed the word table, T-A-B-L. Now as soon as I hit E, it's going to give me a table. Bam, table. And then I can plot, okay, so year zero would be 0 years after 1960, then year 10. And watch this. All I'm doing is hit enter, 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 enter. It already knows I'm counting by 10 years of 10. Right? I could plug in the first population here, right? Okay. So then I just plug in these numbers. Now, I did move the decimal over just to fit this on the graph. Otherwise, there's probably a way to like, skew these axes so that it all fits on the page, but I was having trouble figuring out how to do that. So this number right here actually represents the population 502,000. So I just moved the decimal back so it shows 50. You guys get the idea, right? Right. Anyway, I scaled everything accordingly. And yep, looks like the population is decreasing as the years are passing, something like that. Now, I was looking at these dots saying, I think I could model that fairly well with a straight line. So in terms of a regression, this would actually be a linear regression. So it looks like this. Now, again, I'm going to exit this out, get rid of this line, and show you guys from scratch how I do that. So boink, goodbye. So click down here. I'll say y_1, then right arrow, then the tilde, and this will set up, it'll model the regression for me. A as a coefficient, leading coefficient, x _1. And then, well, here's where it depends what kind of curve you want to make. Now, I'm going to do to the power of 1 because I want a linear regression. Okay. Now, that black line does not look very good, right? That does not model that data, right? But it's about to, because all I have to do is plus b, and bam! Oh, look at that line right there. Now, that line cuts right through those dots. Okay? And so I'm thinking, as time passes, okay, the population keeps going down. Right? And what if I want to do this? What if that, maybe I want to model this with a parabola, maybe. Let me try that. So what if I change this to B and change this to C? Right? And then what if I want to model a parabola? I'm saying, so I'm going to go C x _1 to the power of 2, and then plus point. Is that not, why is it showing upside down? Oh, I wasn't expecting that. Here, let me go another one. Oh, because I have two C's. Oops. Okay, yeah, that looks much better. Much better. Okay, AX to the power. Okay, yeah. Now that black curve is now a true parabola. Actually, I think that fits the points even better, doesn't it? Yeah, something like that. Okay, so you do have to use a little creativity. You have to say, do I want a straight line regression, a linear regression? Do I want to fit a parabola to this? Right? What kind of curve would best fit the data points? And then Desmos will do it for you. I know for linear regression, I forgot to mention this earlier. I know Microsoft Excel, you can also create a linear regression. It probably does parabolas too. I've never done that in Excel, but there's Desmos, you can do it. All right, so all right, leave this example. All right, so just like that. And of course, they'll tell you what A, B, and C are. Okay, I had to show that too to make that exact parabola. So you can write y equals 0.003815x squared plus negative 0.59x plus 50. Right? And of course, move the decimal over 4 places if you like, right, to tell you the population. All right, so we got that. Boom. Right, so there's some more examples like that. They just had different examples, right? Volunteers by month. We got farms as a function of year. We got parks. Right? Yeah, so lots of examples, right? I'm sure time could be taken along. Actually, all these are like by year or month. There's some time taken along. There's some number or something changing. You can fit with some regression model. So that's pretty cool. Right, I got a few more examples here. Use a graph calculator to estimate the coordinates of the extrema. Okay, so we're kind of going back to basics here. See, x to the 3 plus 3x squared. Oh, okay, I see. They're actually prompting you to use Desmos in this case. X to the power 3 plus, oh, here, let me make that one Desmos. Ba-bam. So type that in, gives me this red curve, zoom out a little bit, scroll down, zoom out. Right. Looks just like that. And the book wanted you to estimate the coordinates of the maxima and minima. Right, so here's the maxima or a maximum, right? This would be a local max. So it's a coordinate negative 2.7, comma 12.4 about. And there's this local minimum here at the coordinate about 0.73, negative 8.39. Yeah, so it's pretty close, pretty close. Right? You could also say, okay, here's a y-intercept. I see three x-intercepts, boing, boing, boing. Right? Yeah, you're allowed to have up to three x-intercepts because this says degree 3. Right? So it's all there. It's all there. All right, point. Next example. This canister. I think on the very first week of school, this was one of the examples that I photographed for you guys there because I thought it was pretty cool. So there's some. This looks like a little pill capsule, doesn't it? And there's some radius they're going to call x, and they want this length, well, just the straight part to be x plus 3. Or I think, yeah, that'd be millimeters. So x plus 3 millimeters. Okay. Use a graph calculator uh, to represent the volume of the canister because x could be kind of anything, but you can make x equal to 0, although that wouldn't be very good because I think this volume would just shrink to 0. You know, I'll put that up in the graph and I'll back up that claim. Okay? But what if x was 1? Well, that would make this length right here like 4 units, like 4 millimeters, and this would have a radius of 1 millimeter. Okay? What if you make it x really big? Like, what if x was 1,000? Well, now this would be uh, like 1,003, and this radius would be 1,000. Okay. So you can imagine that this thing sort of proportionally changes shape as you change x compared to the 3, something like that. So what does that look like on a graph? Right, so I just pop that expression right into Desmos, and it looks like this. Right? And you can't really have a negative x value, right? You're not going to have like a negative dimension on this pill capsule shape, right? So really, I think the applicable domain is x starts at 0. Oh, okay. I was going to back this up with the graph too, this point right here. So if x is 0, then you have 0 radius, so you have 0 size. Right? So 0, 0 would be a point. But after that, what if x is like 1? Well, you could plug in 1 and it would tell you the volume in cubic millimeters, right? And it races up real fast. There you go. So it's really just this part of the curve right here, right, which zooms up pretty fast right there. Yeah. So that's it. All right. So that's that one. Wait, make sure I answered whatever question they asked. Use graphic calculator to sketch a model. Okay, boom, did that. What is the domain? Explain the restrictions that it would apply. Okay, so I think I said that too. Yeah, so I said the domain should be 0 to infinity, and the range for that would also be true. We're just looking at this part after the origin. Right. Okay, so I got that. Yeah. This we got a pill like the size of the universe. Ooh, just keep going. Okay. Um, construct an argument. What type of polynomial best models this data? Right? So all these, you guys see all the scatter point, all the scatter plot data. I did pop that into Desmos ahead of time. I got that. So this goes up to, okay, that's a different one. I think it's this one right here. Here we go. This one right here. Okay. Now, if I go back to the book picture, okay, you guys kind of see here. You have to kind of zoom back a little bit and see the big picture. You guys see here? Gotta point down here. It goes up. It like turns up, and then it comes back down, and it goes back up again, and it comes back down. Okay? So I think I can model this with a fourth degree polynomial. Right? 1, 2, 3, 4. Like 4 type motions. Okay. Okay. So x to the power of 4 or something. And the leading coefficient would be negative because it's like an N shape or an upside down W. Right? So I think it'd be like negative x to the power of 4, plus something like that. So back over to where I plug this in. Right. So I plugged in all those points. So it looks like we're counting by quarters. So -1, -8. So that's this point way down here. Point. That was the first point. Right. And then I plugged it in. So this matches exactly, except for this black curve. This black curve wasn't there to begin with. Okay, I showed you guys a few examples how to do this. You see how I did? I chose a fourth degree polynomial. So you do y underscore 1, and then you put the tilde, and then ax 1 to the 4 plus bx 1 to the 3 plus cx 1 to the 2 plus dx 1. Right? Am I missing something? No! Did not mean to do that. Hang on. Here, I'll reconstruct this from scratch for you guys anyway. Y underscore one. Nope, stop there. I didn't mean to hit the X. Okay. I was thinking I had a y-intercept also. It may not have been shown. Y underscore one. Right, then right arrow key, tilde. Right, then A X underscore one power four. I would like to have a fourth degree polynomial. Okay. Plus B X to the three plus CX to the two plus DX. I'm doing underscore one on all of these. Right? Well, to the power of one, I could just leave it like that. Okay. Now I would like to, yeah, okay. Now if I stop right there, you see, okay, it doesn't really fit through those points until what I'm about to do. One more thing. Plus, I need to add sort of an intercept. And I would almost want to say E, but remember, E represents 2.718 in this calculator. So I'm going to type F. Bam! Look at that. Oh yeah. Oh yeah. Look at that. Okay. So now this red curve really fits that data really nicely, doesn't it? I wonder if it's exactly or something like that. It tells me exactly what A, B, C, D, and F are. Ooh, yeah, like that. Oh, and it's just like I told you guys. I said this leading coefficient would be negative. It is. It's like negative 5.0 something. Yeah, yeah, because it's like an upside down W or like an M type shape. Yeah, fourth degree polynomial, negative leading coefficient. There it is. It's all right there. It's all right there. Okay. See, forecasting. Table shows number of deliveries a grocery store has made since they began to offer service. So we got year one all the way to year eight. And the number of deliveries goes from 60 all the way up to over 300. Ooh, looks like it's steadily growing. Like, okay, it dips a little bit here, goes down a little bit, but then it kind of comes back up at the end. So it goes up, goes down, then comes back up. Now, I'm saying that verbally just by looking at the table data. But see, I think I popped this into Desmos. Yeah. All right. Now, this one's a little harder to see because, again, I'm sure there's some way to skew the axes, but I'm working hard to. Here, if you want to make this more visible, watch. I could just, because otherwise it's like skin goes up, down. Right. I could move the decimal over a couple places and say like hundreds of sales. So I'm just going to throw a decimal in right here and zoom in and shrink it. Okay. And this will be a lot easier to see. And then, okay, so I'm counting by hundreds. See, I just moved the decimal two places. Right. So then if I zoom in right here, yeah, there we go. There we go. See, the number of sales in hundreds. So year one, I'm using X as one. Okay. So it goes up, then it comes back down, and it ends even higher than it ever was. Okay, so that's nice. So do they want you to create a polynomial from that? Use a scatter plot curve um, and a curve of best fit to determine the number of goods the store can expect to deliver 10 years. Ooh, 10 years out in the future. So we're going to predict. Right, so yes, I need a polynomial because we're going to predict at year 10, what should the sales be? Now, my mouse cursor, I think if I have a third degree polynomial, so it goes about like this, I'm going to make a guess. I'm going to guess around, oh, maybe 7 or 8. And those would be hundreds of sales, right? About 700 or 800 sales. So let's try it out. Let's do y underscore 1 and then tilde, and then a x underscore 1. Right. Let's go with third degree polynomial. So power 3. Okay, now let's go on down the line here. Plus bx to the power 2 plus cx uh, underscore 1 to the power 1, or okay, you have to type that, and then plus d. Right? Oh yeah, look at that black curve right there. Yeah, it really matches that data nicely, doesn't it? Oh yeah, oh yeah. So, all right, so I can look at this graph and I can estimate. Okay, so 10 years out, that's right. It's pretty close to where that mouse cursor is. About 10. Okay, remember these are hundreds of sales. So 10 hundred, that would be like 1,000 sales. Sales, is that what this is? Yeah, okay, grocery store deliveries. Right. So 10 hundred, because I'm looking at this point right here, about 10 hundred, that would represent 1,000 grocery store deliveries at year 10, right, after 10 years of service. Yeah, that's it. Right, so 1,000 sales. I'm gonna go with 1,000. So we can forecast into the future. Ooh, forecasting. Yeah, future prediction. Okay. And finally, last one I'll do with you guys. Number 31, create sketch graph with an odd degree polynomial function with 6 extrema um, and a relative extreme at y equals 0. Okay. So, so number 31. All right, so let's get a xy set of axes. Okay. It just says a relative extrema at y equals 0. Well, if y equals 0, that means it would be touching the x-axis of its own place. That's all, right? So I need 6 extrema, and it needs to touch the x-axis of its own place. That's that very last condition it says right there. Can I do something like that? Let's go. There's a relative max right there. There's a relative minimum right there. I'll just make that one touch the x-axis because it said a relative extrema. Right. So there's 2 extrema. Here's 3 extrema. There's another max. Here's 4 extrema. There's relative min. Here's 5 extrema. Another relative max. And how about this? Let's go crazy. We're way down here, right? And then 6 extrema. And so I see 1, 2, 3, 4, 5, 6. 6 relative extrema. I just dotted them all, right? That's all I want you to do. That's the whole thing. Okay. Now, if I were to go an extra step, say, I wonder what the a potential equation of this polynomial could look like. Well, it does have 6 extrema. See, it goes down to the left and up to the right, so it's like 1, 2, 3, 4, 5, 6, 7. You guys see 7? Okay. So it has to be at least x to the 7. So I'm going to say f of x, or y if you like, equals some number times x to the 7 plus dot 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 dot. The next to the 6, x to the 5. So here, a little more specifically, you might get, I guess, f of x equals like a x to the 7 plus b x to the 6 plus c x to the 5 d x to the 4 f x to the 3 g x to the 2 h x plus how about k? Yeah, right. Where a, b, c, d all the way to k could represent numerical values. Right? And I know a would be positive because I just want to go down the left and up to the right forever. Right. Right. So there you go. Okay. Graphing polynomials.